Okay, there's one last section, provided some notes for you here, but what we're going to do for an experiment is create the entire probability distribution. I think it's something useful that you can do. A probability distribution would be something like this, where you have a listing of all the outcomes, and then you have a listing of all the corresponding probabilities. This was problem number 71 in there. But if you can, in an experiment, if you can generate this table, which is called a probability distribution, then you can solve a lot of probability questions if you can generate this. And this one comes directly from the tree diagram. The big difference here is that for our problems, the possible X values that we have, so the way that I would write this would be, these are the outcomes. X1 is an outcome, X2 is an outcome, and so on. Oh, yeah, so they gave subscripts. And then the probabilities that go with them. The difference in this section is that the outcomes are going to be numerical. In this example that I showed you, the outcomes were not numerical. They were characters like RR and WW and RG and that kind of thing. What you're going to notice about a probability distribution like this is that every probability has to be a number between 0 and 1. Okay, all of these between 0 and 1. And when you add them all up, you have to get 1. If you have a table like this that lists all the outcomes and numerical outcomes and their corresponding probabilities, and these two conditions hold, then you have completely defined a probability distribution. All of our problems today, there's going to be one result, and they all start with a table like this. So either the table is going to be given to you, or you have to figure it out from the word problem and generate it yourself. And the one result we have is the expected value. And what we're going to do is we're going to take this numerical outcome and multiply it by the corresponding probability and get a product. So if I just extended this table, I'm going to take each numerical outcome and multiply it by its corresponding probability. So if I did that here, it would be X1 times P1. This one here would be X2 times P2. That's what they're telling you right here. Then, to get the expected value, you're going to sum up, add together all of these numbers in this bottom row. And the interpretation is this is the expected value, that in the long term, in this scenario, what would you expect the X value to be? That is, what is the long-term average of X? And the answer to that is the expected value. All right, so this is it. I mean, this is the extent of the notes. You've got one result, you need the table. So let's take a look at a bunch of examples. I don't want to suggest that these problems are not hard, because they are. It's kind of hard to figure out what the table is a lot of times. But it's nice if the table is given to you. And unfortunately, we cannot read these very well. So I'll draw them in. So there could be problems like this, where they just give you a table. Here is your X, and here is, I would call it your P of X, the probability. All right, and so we're going to add another row where we multiply the numerical outcome by the corresponding probability. The first thing that we should check is that when we add those 5 numbers together, the probabilities, you can see that they add to 1. Sum of probabilities equals 1. You can see all probabilities between 0 and 1. So if those two conditions hold, then you've got a probability distribution, and then you can go forward with the expected value calculation. Now, in this problem, they said, if the probability distribution is given. So they're saying that this is a probability distribution. So you really don't have to check it, but if we just checked it anyway. All right, so we're going to multiply these two numbers, negative 0.2, multiply these two numbers, negative 0.2, multiply those two numbers, well, 0 times anything is 0, and do this consistently throughout. Now, the sum is going to equal to negative 0.2 plus negative 0.2 plus 0 plus 0.2 plus 0.2. You can see pretty quickly that that is 0. So the expected value is 0 in this case. And that's all you're asked to calculate. All right, I want to show you how to do it on your calculator, just in case you get messy numbers and you don't want to do all these multiplications. Here they are. What we're going to do is we're going to put all the numerical outcomes in list L1, and we're going to put all the corresponding probabilities in list L2. All right, so negative 2, negative 1, 0, 1, and 2. Right, the calculation is pretty trivial with this example, so normally we wouldn't use the calculator, but and then put in the probabilities, 0.1, 0.2, 0.4, 0.2, and 0.1. So you've got the numerical outcomes in first list and the corresponding probabilities in the other. And then what the expected value is like the long-term relative frequency. It's like the average. If if this was a game, if you played this game over and over and over and over again, what would you expect the long-term average to be? And in statistics, the average is the mean. So that's what we're going to calculate. We're going to calculate the mean. And the calculator function you want to give, and you'll look at this in a lot more details if you take a stats course. But we're going to calculate the single variable statistics. And you need to put in list 1 as your X list and L2 as the probability list. And then enter. And your calculator will calculate the variable and statistics for the expected value, or the mean is X bar. All right, so here's what it's going to look like. Once you have the data in there, you can quit to go back to your home screen. And then, since we're going to do a statistical calculation, you want to go into the stat menu and then go over to the menu that says you want to calculate something, the middle menu, and there you see the single variable statistics right at the top. So if you select the single variable statistics, some of you, I have an old calculator that makes me just type everything onto the home screen. If you have one of the newer calculators, then the X list will be L1 and the frequency list will be L2, even though it's not really a frequency. And then just hit enter. And notice that the X bar that it reports there is 0. And that's the number that you want to identify. Expected value, 0. All right, so the rest of these problems are all applications. And they all require that the very first step you do is to draw that table, because in order to calculate the expected value, you have to have a listing of all the outcomes and the corresponding probabilities. All right, so let's take a look. It's pretty bad. All right, I'll read it to you. You draw and keep a single bill from a hat that, so you can draw this money and you can keep it, right? You draw and keep a single bill from a hat that contains $1, a $10 bill, a $20 bill, a $50 bill, and a $100 bill. What is the expected value of the game to you? So you just get to draw one bill. So here it is. I'm going to draw a little picture. And we got a $1 bill in there, and a $10 bill, and a $20 bill, and a $100 bill, and a $50 bill. Now, all of those bills have the same texture, they all have the same size, and when you reach into a hat to grab one of them, each one has an equally likely chance of being selected. There are 5 different bills, and so the probability of selecting any one of those bills is 1/5. So here is the grid. Outcome can be a $1 bill, a $10 bill, a $20 bill, a $50 bill, or a $100 bill. Notice they're all numerical outcomes. And the probability of getting any one, since we're just going to randomly select one from the hat, each one is equally likely to occur, to be 1/5. Here's all the work. This is all the work setting up the problem. If you can get to this point, then the rest of it's just going to be, you can either enter it into your calculator, or you can just add another column, multiply, 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 and multiply. And then look at the sum. So we add 1/5. All right, 1/5, that means 1/5 of $1. So that's 20 cents. Plus $2, plus $4, plus $10, plus $20. 20, 36, $36.20. Okay. Now later on, they're going to ask you some questions like, well, what if it costs $50 to play this game? Would you play it? You pay 50, and on average, you're going to take in 36.20. So if every time you play it, you got to pay 50 bucks, then on average, every time you play it, you're going to lose $14, about $14, a little bit less. Now, if they charge you $30 to play the game, then you would probably try to play as many times as you can, because you would be expected to win $36 after having bet only 30. So on average, you would make $6.20 every time you play. Yeah, so that's expected value. All right, let's take a look at number 14. All of these are going to be different contexts. In some of them, the grids will be, or the tables will be longer, like 5 entries. Sometimes they'll be smaller, sometimes they'll be larger. You're drawing a single card from a 52 card deck. If it's an ace, you win at $104. Otherwise, you get nothing. What is the expected value of the game? All right, so you're going to have a lot of these expected value problems. So you have 2 outcomes. You win or you lose. Now, win and lose are not numerical. So you somehow have to put this in terms of money. If you win in this game, what do you win? $104. If you lose, how much do you win? Nothing. So we've converted these 2 outcomes of win and lose to our X value, which is our numerical, what we're trying to calculate the expected value of. So in this case, X equals my winnings. And so the expected value in this context is always related to what the meaning of X is. So if X is expected winnings, or is the winnings for each of the 2 scenarios, then the expected value, I think our author calls it E, is equal to the expected winnings, my expected winnings. All right, and then the probability. And so you have to rely on what you know about drawing a card from the deck. You win if you draw if it's an ace. So there are 4 aces in the deck out of 52 cards, and there are 48 non-aces out of 52. So you lose with a probability of 48 over 52, because that's how many non-aces there are in the deck. 48. And the probability of winning is only 4 out of 52 because there's only 4 aces. All right, so you've defined the x and the p of x. So the next thing to do would be to multiply those two. And 0 times anything is 0. So it looks like all we have to do is to take those two numbers and add them together. Okay, now I know why they gave 104, because 104 cancels 52 evenly twice. So you have 2 times 4. So this part is 0, this part is 8. 0 plus 8 is equal to 8. So you draw a single card, blah, blah, blah. What is the expected value of the game to you? All right, so the expected value is $8. And what that means is that every time you play this game, you can expect to win $8. You will never win $8 on any one try. You're either going to win $104 or you're going to win nothing. But in the long run, you can expect, on average, to make $8 every time you play. So if you played this a billion times, you would expect, you're going to either win $104 every single time or you're going to lose. All right, so you'll have a bunch of zeros, then a 104, bunch of zeros, 104. But if you add up all that money, if you play it a billion times, on average, you win $8 every time, you'll walk away with, on average, $8 billion. That's what that means. So if you just look at the first two problems, word problem, table, calculate expected value. Word problem, table, expected value. You need a table for every one of these. That's where all the work is involved. All right, well, we're dealing with games of chance. Maybe we'll do one more. And this one says on 3 rolls of a single die, where the outcomes are 1, 2, 3, 4, 5, 6, you will lose $10 if a 5 turns up at least once, and you'll win $7 otherwise. What is the expected value? So this is another one that's like number 14, where you have 2 outcomes. You're either going to win the game or you're going to lose it. So what's tricky about these problems is, calculating the probability sometimes. Not too bad when you're just drawing aces out of a deck. Okay, so let's let X be, once again, my winnings. And then when I calculate the expected value, again, it's going to be my expected winnings. And that's what they're calling the value of the game. Okay, you will lose $10 if a 5 turns up. All right, so you'll lose $5 if a 5. And the way we indicate a loss is with a negative. So you lose $10 if you're going to lose. And you'll win $7, so we'll indicate that with a +7. Otherwise, if a 5 turns up at least once. All right, now these probabilities that we calculate rely on stuff that we've done in the past. And again, this is another one where they say at least one or at least once. And so there's just 2 probabilities, and I know these probabilities, when you add them together, have to add up to 1. So if I can figure out one of the probabilities, I can then subtract it from 1 to get the other one. Okay, so what I need to know is, what is the probability that a 5 would turn up at least once? So I'll write it descriptive like this. What's the probability that a 5 appears at least once in 3 rolls? Now I'm going to use the complement rule. The probability of at least once is 1 minus the probability of none. And in this context, none means no 5s appear in the 3 rolls. Now, if this is not clear to you, you could draw a tree diagram right? 5, all 3 outcomes. First roll, second roll, third roll. You have the 6 rolls. 6 rolls, it would be a 6, and then a 6, 6, 6, 6, 6, and then 6 from there. So you'd have 216 possible outcomes. But this one we can calculate. 1 minus the probability. I don't want the probability. Now, I normally wouldn't draw this tree diagram if I was doing this problem myself, but I want to try to encourage you to draw a tree diagram as much as you can, because if nothing else, you know how a tree diagram works. And if you can draw the tree diagram, you can eventually get to the solution. Now, I could write, instead of not a 5, I could write, 1, 2, 3, 4, and 6. So we'd have all 6 outcomes, but it's going to get really, really cloudy after this. And if you roll the die one time and then you roll it again, knowledge of what you got the first time does not impact the roll of the die in the second time. It does not change the probability of getting a 5 on the second roll. So these events are independent. So the probability of getting a 5 every time is 1/6, and the probability of getting something else is 5/6. And that's going to be consistent throughout. And I'm not even going to write, but if I did, I would have 1/6 and 5/6 on every other pair of branching. But I'm going to stop here because remember that the probability we're trying to calculate is the 1 minus the probability of no 5s in the 3 rolls. So you can't have a 5 on the first one, and you can't have a 5 on the second roll, and you can't have a 5 on the third roll. So you have to follow this path. Not a 5, not a 5, not a 5. Every other single outcome in this experiment would contain at least 1 5. Any other branching, of course, if you go up here, your first roll is a 5. So everything up here would contain a 5. Not a 5, but if you go over on this branch, then all of these outcomes will have a 5. Not a 5, not a 5, and you don't want to go there because that's a 5. So the only outcome where you don't have a 5 is that very last one. So that's the picture. And then the way we would do it is we would take 5/6 times 5/6 times 5/6. Basically, the probability of no 5s would be this branching here, where we multiply. So all of this just to calculate the probability. We're not even close to the expected value yet. But 1 minus 5 divided by 6 to the 3rd power. 0.421. And if we want to convert that to a fraction, that's 91 over 216. All right, so this is the probability of getting a 5 at least once. And you would lose $10 if a 5 appears. So the probability that that happens is 91 over 216. And so the probability of winning would be 1 minus the probability of losing. It's 125. I should have known that. 125. All right, so then the expected value is equal to, we're going to take the numerical value of x and multiply it by the corresponding probability. Add that, -10 times the corresponding probability. So this is what I was talking about. Sometimes these numbers are a bit messy. But again, you can evaluate this on your calculator. And this is the amount of money that you would win. So I would leave this one as a decimal. 7 times 125 divided by 216 minus 10 times 91 divided by 216. All right, now comes the interpretation. We defined X to be, actually, these are dollar amounts. You win 7, you lose 10. And so when we calculated the expected value, we found this number. And that number is the same unit, has the same unit as our x's. So this number here is the number of dollars. And so, you know, usually we just round to the nearest penny. And so we would say that we can expect to lose 16 cents on average every time we play this game. I'll just call it a play. We're playing the game. For each play, you're going to expect to lose. So this is a game that has a very low expected value. So this is a game like blackjack or like craps at the casino, where you can sit there all day and you can play a very you know, like probability of getting a 7 or something, or an 11 in craps, and you can play for a long time at one table. And if you do lose, you're going to lose $10. But if you play for a very, very, very long time, it's only going to cost you about 16 cents every time you play it. So people can, you know, win 7, lose 10, win 7, lose 10, going to win 7 more often than they lose 10. So on average, they're going to lose 16 cents. All right, let me try to give you some variety of questions. You can see, again, the hard part is setting up the table. And sometimes calculating these probabilities are going to be difficult. Now let's see what we have on the next page. I'm not going to do all the problems on the notes. I don't have time here, but I'll do them after class so you can refer to these. Raffles are losing propositions, right? The purpose of a raffle is to raise money for a charitable organization. So when you calculate the expected value of playing a raffle, yeah, it's going to be negative. That means you're going to lose. But you know that going in. Same with casino games. All right, so number 40, 10,000 raffle tickets, and they're going to sell them for $2. So this organization, they want to take in $20,000 because they're going to sell 10,000 tickets for $2 each. So they're going to take in, and the amount of money that they're going to give out in prizes, they're going to be 2 prizes of 1,000, so that's 2,000. There's 4 prizes of 500, so that's another 2,000, and 10 prizes of 100, that's another 1,000. So it looks like they're going to take in 20,000, and they're going to give out 5,000. So at the end of this raffle, the organization is going to make 15,000. And all this math is done before the raffle is actually held, because the organization wants to know that they're going to make some money. Okay, let's look at the expected value of the raffle if you purchase 1 ticket. All right, so what's the expected value for 1? So once again, we're going to identify the outcomes, and they told you all the possible winning amounts. All right, now when you consider your winnings, this is X, your winnings, here's the first example where you have to actually pay to play the game. Now, when you buy a raffle ticket for $2, and let's say you won the $1,000 prize, they don't give you the $1,000 and your $2 back, they keep your $2. So you have to figure this all in when you're calculating the expected value. You cash out $2, cash in $1,000. So even if you win the $1,000 prize, you really only won $998. So your winnings then would be $998. So let's go through each one. There are 2 prizes of 1,000. So I'm going to put 1,000 up here. And then the winnings would be $998. There are 2 of these winners. 2 prizes of 1,000. There are 4 prizes of 500. So if you win one of those 4 $500 prizes, then you're really going to only take in $498. $2 less than the 500 you won. And then there are 10 of these $100 winners, but those who win 100 had to pay for their ticket, so they're only going to take in $98. Now, don't forget about the loser. The losers. Most people who buy a lottery ticket will not win. And we know that there are 2 $1,000 winners, 4 $500 winners, and 10 $100 winners. And if you add those numbers up, you get 16. So 16 different tickets are winners. And they are selling 10,000 tickets. So of the 10,000 total tickets, 16 of them are winners. That makes 9,984 of them losers. And what's somebody's winnings if they lose? Well, they win $0, but they had to pay the $2, right? So they actually win negative $2 because they bought the ticket. Okay, now the probabilities. There are 2 tickets out of the 10,000 that would lead someone to win the $1,000 prize. There are 4 tickets out of 10,000. 10 tickets out of 10,000 that would win $100, and 9,984 out of 10,000 would be the number of tickets that are losers. All right, so for this one, I'm going to type into the calculator just because it's much quicker. And you can see that it takes really just 30 seconds to type this stuff in. All right, so 998, 498, 98, and negative 2. And I somehow got out of the wrong screen. 998, 498, 98, and negative 2. So I'm putting the X values in the first one, and then I'm going to jump over here. Now, I have to type in 2 divided by 10,000, and it's going to give me that amount in scientific notation. That's okay. 0.0004, 0.001, and 0.9984. So this is how these fractions will appear in your calculator screen. So, and then I have to go and calculate one variable statistics, L1. This is the same thing I typed in before, and there you can see it. The expected value is negative 1.5. All right, so the by hand approach, these are the numbers that you'd have to add together. And if you do that, you get negative 1.5. And remember that this is a dollar amount. And so what this means, and the way we interpret this, is that every time you play the game, you can expect to lose $1.50. Okay, remember you have to come up with $2. So it's not going to cost you $2 every time you play it if you play it a lot over the long term, because every now and then you're going to win. Most of the times you're going to lose, but every now and then you're going to win. So on average, every time you put that $2 up, you're going to lose $1.50. But we know this. You're going to lose 3/4 of your money.